So the second speaker of the session is Erik Hjelmvik. He's the CTO of Netnod. He works with incident response and network forensics. He started analyzing network traffic from a security perspective while working at the R&D department at a major energy company, where he focused on SCADA and industrial control system security. And he's also worked as an incident responder for more than 5 years at the Swedish Armed Forces CERT, where he worked with network forensics and network security monitoring. So please welcome Erik to the stage.
Thank you, Rob. So, I'm going to talk about something called man-on-the-side attacks. Who knows what a man-on-the-side attack is? Anyone? Okay, so who knows what a man-in-the-middle attack is? Okay, good, lots of hands. So let's start there. This is a way to visualize what a man-in-the-middle attack is. So we have Alice, who's trying to talk to Bob, but somehow Mallory gets in the middle. So Mallory can intercept all the messages between Alice and Bob. Mallory can replace messages between Alice and Bob. He can inject new messages or just remove the data being transferred. So this way, Mallory can read out passwords or secret messages or change secret messages into something else. While a man-on-the-side attack is more like this. Here, Mallory is not really in the middle. He's on the side. So he can still intercept messages between Alice and Bob. He can also inject additional messages into this communication. So you can send a new message, but he cannot remove any signals, he cannot remove messages, and he cannot modify any messages. So that's the important limitation when doing man-on-the-side. The term man-on-the-side attacks became widely known after Snowden leaked a lot of slides about NSA's quantum insert project. And this is one of the slides he leaked, and that was published in Der Spiegel. So what's happening here is that, let's see if I get a pointer. We have a user somewhere in the Middle East who's trying to visit a website somewhere in Europe. This user in the Middle East visits this website through a satellite link. The GCHQ is here. They have a satellite dish, so they can receive the signal, because satellite traffic is broadcast. So basically, you just have to have a satellite dish in the right region, and you can read this transmission. And for some reason, they decided, yeah, they send the signal to NSA, and they say, this is our target. This is the person we want to infect. What the NSA does then, they inject a malicious response back to the user in the Middle East. And you can see they inject the response somewhere close. They don't inject the response through the satellite link. And that's the second reason why the NSA loves satellites, because one, it's broadcast, but two, it's very high latency. Especially geostationary satellites, they're very high latency, because the NSA have to send their response to the client before the actual response come up and down through the satellite link. So since it's a slow link, they have a good chance of actually beating the proper server response with their injected response. And that's how they, well, that's on a top level, that's how they try to infect the user. So a different question. Who knows about the company, the hacking team? I see a few hands. Okay, next question. Who more than I thinks that this guy looks a lot like Zlatan Ibrahimovic? Right? Well, actually, this is Zlatan Ibrahimovic. This is Zlatan. This is the hacking team guy. This is Zlatan. So totally different persons. But anyway, sorry about that. But the hacking team, what they do is they sell a service or technology to infect people's computers or people's phones so that they can extract information from them. For example, data that would otherwise be encrypted. But what's interesting with the hacking team is that they themselves got hacked in 2005 by a guy who calls himself Phineas Fisher. And one of the things that Phineas Fisher did was that he released email communication, internal communication within the hacking team. And there's one very interesting email thread where they're talking about the NSA quantum insert program. So this guy, Marco Catino, says that, hey, there's a cool link here about the NSA doing quantum insert. And he says that it's very similar to NIA's features. So apparently they have something called NIA or NIA that's similar to quantum insert. And then this guy, Alberto Ornaghi, who's one of the brains in the hacking team, respond and say, yeah, there's still our technology and ideas, but what can we do? Sue them, ha ha ha. This is proof that our idea was good. And then finally, this guy, Serge Boone, chimes in and say, yeah, we can sue them for infringing patent, smiley. So I was like, what? They have a patent for man-on-the-side attacks? That's cool. So I Googled a bit and found this. So they actually have a patent for man-on-the-side attacks. So for some reason, the hacking team developed this technology alongside NSA, because this was sort of in the same time frame. And if you scroll further down in the patent, there's a very good slide that shows how the man-on-the-side attack works much better than any of the stuff that Snowden revealed. So I'm going to step through this carefully. So you can see it starts with a GET request. So we have on the left, we have the target. That's the person the hacking team are trying to infect with malware. This person is trying to visit a server, but somehow the hacking team have their man-on-the-side product in the middle here. So first thing that happens is that the client sends a GET request to say, I want to download this exe file from this web server. They sniff this packet and say, okay, now he's doing a GET request for an exe file. That's interesting, let's use this. And since they're only sniffing traffic passively, they cannot block it or do a man in the middle of it. Instead, this packet will make it all the way through and to the proper server. But they can inject an additional response. So they spoof a response packet, and they have to make sure that their spoofed packet arrives at the client before the proper response. So they spoof a response, and you can see the response they're spoofing is that they're sending a 302 found, which means that, oh, you're looking for this exe file. Well, we moved it. It's somewhere else right now. And somewhere else in this case is a fake subdomain. So the user is trying to download the file from example.com, but they're saying, oh, go look at XYZ at www.example.com. And this subdomain XYZ is a subdomain that doesn't exist. They just make up a completely new subdomain in this location header. Then, of course, the proper server will send the 200 OK and the exe file, but the client will actually ignore this 200 OK from the server because it has already received the proper response from the injected packet. So it will not care a bit about the response from the server. So instead, the client will continue and say, hey, I need to go into xyz.www.example.com to get this exe file that I really want. But he doesn't know the IP address of that server. So he's going to do a DNS lookup. Again, the hacking team are sniffing the DNS requests. So they can see, oh, now he's doing a lookup for this fake subdomain we sent to him. And this DNS lookup will go make it all the way to the DNS server. But again, the hacking team can spoof a packet, so they can inject an additional response. So they inject their own response, and again, they have to send the response to the client before the proper response. But this time, they give the client an IP address that the hacking team themselves control. So they give them an IP address to a server that they run. And shortly after, the proper response will come and say that there will be an NX domain response saying, basically, there is no such domain with that subdomain name. But the client won't care about the NX domain because the client has already received a proper DNS record with pointing to a hacking team server. So next thing is that the client connects to hacking team's actual server now, saying, hey, hacking team, or he doesn't know it's hacking team, he believes it's just subdomain of example.com, saying, now I want to download this exe file. Hacking team server say, hey, great, he's trying to download this exe file. Then they go ahead, connect to the real server where this exe file is actually located. They download it from the real server, and they modify the file. So they embed some piece of malware or some type of exploit into this exe file and send it back to the client. So the client will, if you look at this from the client's perspective, the client clicks on the link on this proper valid domain for this exe file where you're supposed to download this binary. He gets an exe file, he runs it. He doesn't really notice all these directs and faked responses. But from a defender perspective, what you want to do is, how would I detect this? How would I detect this type of attack? And there are two places I'd like to look. First place is that in this GET request, there's actually two responses coming in. The TCP/IP stack will actually ignore the second response, but only care about the first one. But if we look at it at a packet level, we will see that there will be 2 packets in the same TCP session with the same TCP sequence numbers, but they will have different data in them. So that's something we can look for. Second thing we can look for is on DNS traffic, because we will send 1 DNS request, but we will get 2 DNS responses for that one. And those responses will have different contents. So one will, in this case, one of them points to an IP address, the other one says the domain doesn't exist. So if we start with the DNS, it will look something like this. So I created a definition of, okay, what do I consider a DNS injection? So I say that it has to be 2 DNS replies where both DNS replies have the same source and IP, and source and destination IP. They have to have the same source and destination port, and they have to have the same DNS transaction ID, or I just call it DNS ID. But the DNS records in the response need to be different. I also said that I need to see 2 such responses within the same hour. The reason I did that is because I wanted to try this on my own network traffic, and I have like lots of historical network traffic from everything I do, and it's segmented by hour. So I just want to look in one PCAP file and see, do I see 2 responses in this PCAP file with the same source and destination IP, source and destination port, same DNS ID, but different resource records within the same PCAP file. So I did this, ran through all my PCAP files, and I got lots of alerts, lots of them. So here's like one of the hours where I had most of the alerts, or I had lots of alerts during this hour. You can see here that this looks like there's Ubuntu machine. You can see here's the queries the clients are sending. So it seems to be a Ubuntu machine running Firefox that's booting up here. So it's the Firefox browser starting on the Ubuntu machine. So it's doing all sorts of lookups. But can you see what the problem, or something that's strange about all these lookups? What do all of these have in common? Can anyone spot it? Yeah? The same address of the, you mean of the client and server? Yeah, and it's the same, like if you look on the port even. So it's the same client talking to the same DNS server all the time, and DNS server is of course talking on port 53, and the client is, for some reason the client decides to send all its queries from port 62,050. So of course you can do this in DNS. You can just pick one port and just stay with that port and send all your queries from that port. But it's not good for several reasons. One of the reasons is an attacker could easily, if they know you're always using port 62,050, they can just inject fake responses to port 62,050, and hopefully, one of those responses will be accepted by a client, so they don't even have to sniff your traffic to inject fake responses. So therefore, the client port is typically randomized. For every new DNS query, you pick a new random high port and do a new query. But in this case, this Ubuntu machine decided that, no, I don't need to randomize the port. I'll just use the same one all over again. But luckily, at least we've got some entropy because the client, we have something called a transaction ID or the DNS ID. So that should be unique for each query. In the old days, you would usually increment this by 1. For each new DNS query, you just incremented the transaction ID by 1. So if we would do that, then that would mean that I would need to have more than 64,000 queries before we would start repeating, and we would get an overlap with the same query ID again. But for the same reason, we're randomizing this, because if we would do this incremental, it would be very easy for an attacker to know which would be the next query ID you're going to use and just inject a fake response to you, and that will be accepted. So therefore, we randomize this DNS ID all the time. But the problem is when you randomize the DNS ID, you will get collisions much faster. So the birthday paradox tells us that we actually only need 300 unique DNS requests if we're not randomizing the port. We will, after 300 DNS IDs, we have a 50% probability of getting a collision in the DNS ID value. And in this case, if we go back, the client did more than 1,000 DNS requests. So of course, there were a lot of collisions here. So I got a lot of collisions. So I realized that, OK, my first script to find DNS attacks or DNS injection attacks, it wasn't good enough. So I had to be more strict. So what I did, that I still said that we need to have the same source IP and same destination IP for 2 DNS responses. They have to have the same DNS ID, different records. But instead of saying they should proceed within 1 hour, I'm saying that the 2 responses need to be 2 consecutive responses without any other response in the middle. So we see 2 responses with everything the same except for the DNS records. Then it's a DNS injection attack. So I ran this again on all my PCAP files. Oops, sorry. And this is what the script looks like. Actually, to say it's a script, it's actually just a bash one-liner. So, but what it does, it's TCP dump, reads a PCAP file, filters on port 53, looks for packet that have a DNS ID field, and the purple parts here, that's the stuff that I want to be the same. So I wanted to see 2 responses where the purple part is the same, and I want the red parts, that either DNS CNAME or DNS A record, to be different in 2 consecutive responses. And if I see that, that's when I alert. So I ran the script, and hopefully I shouldn't get any alert on my traffic, but I actually got alerts. So I was like, what the heck? And what I realized that, OK, I have a different problem now. Because for some reason, I have some DNS clients seem to retransmit the same requests more than once. So they send the requests, and then they send the exact same request again, using the same source port even, and even the same DNS query ID, or DNS transaction ID. So I see 2 identical requests being sent, and normally if you would query for that, like go to my website, like netresac.com, you would get a response saying that, yeah, that's over at 195.something something, and in the second request, you would get a response saying, yeah, it's still over at 195 something something. My script would handle this because, yeah, then the DNS records are the same, so it will not alert on that. But of course, there are many sites where the responses for each request will be different because they're doing load balancing, or maybe there's a content delivery network where they spread out the load throughout a lot of IPs. So in this case, here's one example where this happened. So the blue part, that's the first request, and the white part are the second requests, or the responses from the second request. So there's a service called Crashlytics. So I think there's an app here that crashed for some reason, and it sent some crash information to crashlytics.com. So when it crashed, it does a lookup for each Crashlytics, and it actually does this. It sends 2 identical DNS lookups for crashlytics.com and gets responses, and they look pretty much the same in response, but you can see that the IP addresses are different. They are somewhat different, so they're not the same. So that's why my script will alert on this. But I could see that, OK, but it doesn't seem to be a malicious response, any of these, because they're all hosted on Amazon, just different IPs on Amazon. Although I'm not 100% sure it's not malicious, but that's my best guess. So I'm like, at this point, I felt like this. I'm sitting here trying to find DNS injection attacks, but I'm failing because all of the messiness in how DNS normally behaves. So the normal behavior of DNS is a bit of a mess, so therefore it's very difficult to find the attacks. But at least what you can do is you can, of course, protect yourself against this type of attacks. So one way is, of course, to use DNSSEC. But if you use DNSSEC and want to be protected against these attacks, you have to be prepared to ignore any responses you get that are not signed, or ignore any responses you get that you cannot validate. So you have to really enforce this. Another option, which is becoming quite popular, is to use DNS over HTTPS or DNS over TLS. Then you have a different issue. It's more like, who do you trust? Who do you send your DNS queries to? And there will probably be higher latency also. So it's performance issues as well. And the fourth solution here is run your own DNS server. Don't use anyone else's. Your own DNS resolver. Exactly. But then again, somehow, that resolver doesn't know about everything, so it will have to query stuff. So you have to, it's not really protection, but at least you limit the your exposure. Or you can go extreme and take the advice from DNS Borat and just put everything in itsy hosts, right? It's good for privacy, and you'll be secure because you don't need to use DNS at all. It's very impractical though, so secure but not practical. So, but we had a different place where there were problems. So now we've talked about DNS, but the bigger problem is actually here up on TCP or HTTP, because this attack could have been pulled off without DNS at all. They could have sent just, 302 found, go to hackingteam.com and download this exe file. And the browser would actually go to hackingteam.com and download this exe file. So they actually don't need the DNS. So this is the more important part. And for this 302 found response, what we can do is we look for 2 TCP packets in the same TCP session with the same TCP sequence numbers, but different data. And I've written a script to do this, and it works very reliably. So it's called findject.py. It's available on my website. So it's just a Python script. Please feel free to use it. It's very simple. You just run it with Python and give it a bunch of pcap files in the argument. It will then run through the pcap files and will say for each pcap file, it will say if there's an injection or if there's no injection. If there's no injection, nothing fancy. If there is an injection, it will print a 5-tuple. So the source IP, source port, destination IP, destination port, and it will print a sequence number where there were 2 duplicate packets, and then it will print the contents of the first TCP packet and the contents of the second TCP packet. So you can see that, hey, they're different, right? Then you got a man-on-the-side attack. So I ran this script on my pcap files again. So, okay, hopefully I shouldn't find anything because this is very reliable. But I actually found something. One of the computers was doing a Windows update. So we contacted the server of Microsoft saying, hey, I'd like to download this Windows update. And for some reason, I got 2, and when the bits client, which is used for doing the Windows update, it actually just doesn't download the whole cab file as one big chunk. It downloads piece by piece using something called partial content, doing a range request and gets a partial content response. And when doing this, a few segments in this Windows update were actually different. So I looked at it, and I looked at the data and saw that, well, the file data I'm getting is actually identical in both packets. The only thing that differs is this header, this XHW header. And X headers is something any server can just append, but in this case, I'm guessing it has to do with something about hardware. So I'm guessing Microsoft is running a load balancer, and the parts in purple, that's the parts that differs. So I'm guessing that Microsoft is running a load balancer. My client contacts the load balancer. The load balancer contacts its internal servers and say, hey, servers, who's going to send this piece of Windows update to Erik? And 2 of those respond that, yeah, I've got this. And for some reason, the load balancer let both of those replies back to me. And this was happening. I saw a lot of this behavior during this day, December the 12th last year. And these packets will, of course, have the same sequence numbers. They will have the same file contents, but it's just this XHW header that's different. So, of course, my script worked because it was supposed to detect stuff like this, but it wasn't an attack. A question? Yeah.
What is GMT?
Timestamp? Sorry. Yeah, you should tell them. You mean to have a more precise UTC time zone? Well, out of scope, sorry about this, but I'll be happy to talk about this in the break. So I got a different response. Now this is a different, so I dug deeper into my pcap files, went way back, and I actually got something very interesting in 2016. So I was like, yeah, or what the heck? I don't know how to react to this, but I'm doing a GET request for this 02995.com, and I'm getting 2 responses. And this looks nasty, right? This looks like the examples from the hacking team. I'm getting 2 responses. The first response is at 302 found, which basically says, hey, this file is somewhere else right now. Go to this website, how123.com to download it. It's like, okay. And then I got a second response saying, no, this file is not there anymore. It's on how360.cn. So I got two type of redirects. So I don't know really like which one is the malicious one, which one is the regular, is the proper one. I don't know. So let's just look what these websites look like. What if I could actually connect to that URL? So the first one, it's actually Chinese start page. Looks like this, like basically start landing or start page from a telco provider or something. Okay, seems legit. And then the second one, well, it's a different start page for a competitor of them. So I was like, now I remember. So this is an actual man-on-the-side attack that I triggered on purpose in 2006. So what I did is I contacted this server in China, this 02995, requested this, any file on their server, and what they're doing is that server in China will respond with this move to say, oh, we moved it, it's now on how360.cn, go there. But for some reason, I got this 302 found as well, and that's actually injected by a Great Firewall of China. So on the perimeter of China, someone's injecting a fake response because they don't want me to go to this how360.cn. They want me to go to how123.com, which is, as I understand it, it's a competitor. So they want to move people who are outside China from this company to the other company for some reason. I have no idea why. So, and the reason I was looking at this, because I was validating a research that was done by these guys. So there's a very good research paper called Website Targeted False Content Injections by Network Operators, where they looked at 180 terabytes of data of HTTP traffic from 3 universities and 1 corporation. And they found a lot of suspicious traffic that seems to be man-on-the-side attacks. So to protect against TCP injections, my recommendation is always use HTTPS. So either you explicitly type HTTPS:// and domain name, or you use a browser extension that does that for you, like HTTPS everywhere. Because if you don't type HTTPS, just type www.google.com, you will connect to Google on port 80, and Google will do a redirect for you to port 443. But if someone is doing man-on-site on you, they can see that request on port 80, inject the redirect to a server they control, to hackingteam.com. And you will go to Hacking Team, they will affect you, and then redirect you back to Google, and you might not even notice. But of course, there's a lot of traffic. Even though you do this for a browser, there's a lot of other stuff on your computers, device, phones that talk HTTP unencrypted anyway. So if you really want to block it, you really need to block port 80 traffic in a firewall, which you might not want to do because stuff will break. So that's a problem. It's difficult to really stop all of port 80. And another problem with this is actually sort of a vulnerability in the TCP/IP stack. And there's no way we're going to patch this. This is going to be around anyway. So the best thing you can do is use some type of protocol that enables us to authenticate each message from the other end to make sure that we can actually throw away messages because they're not properly signed. So yeah, that's it for me. Thank you. Any questions?
So we're a little bit tight for time. I suggest if there are any questions, you could take it in the coffee break, if that'd be okay.
Perfect.
Great. Could you join me in thanking Erik for a great presentation? Thank you so much.